Welcome students to your numerical based channel producer classes as PSC where logo can talk the physics. And today we are in the numerical king series HC Verma solutions and students today's numerical series question number 34, 35, 36, 37, 38. Okay, so these 5 questions are based on the chapter electric field and potential, and this is chapter number 29. So students, take a habit of just note down the questions and try and then see the answer. And students, as I say, if you are first in that particular class, then go back to the previous one where all the numericals from 1 to 33 are completed, as well as the all the concepts related with Gauss law, that is for the chapter 30 is also completed. Okay, and for 11th standard it is also completed the first chapter, that is unit and dimension chapter. So this is actually chapter number 3 is running, chapter number 3. So this is chapter 29. Let's start with the numericals 34. So write down first the numericals. First of all, students, I want to say that you have to know the concepts of electric field. So, electric field. What is about electric field and who can create an electric field? Suppose, student, there is a charge Q. There is a charge Q and it can create an electric field. It can create an electrical influence around it. So, if we want to calculate the electric field at a point, suppose this is the observation point. The observation point is r distance from that point charge. So, you have to place here a charge Q0. What is about Q0? Q0 is a test charge. So, test charge. So test charge, therefore the test charge can experience the force of F equal to, from Coulomb's law we know that 1 by 4 pi epsilon naught and then Q naught by R square. So electric field, from the definition of electric field we know that force experienced by this charge equal to F by Q naught, that means 1 by 4 pi epsilon naught and Q by R square. So this is the expression for electric field. And all the numericals are related with this electric field. Electrical field intensity. So what is electric field? An electrical influence around a charge. So if there is a charge, then it can create an electrical influence around it. Since this is positive, then the field lines are along. I can create a diverging field. And if it is a negative, then it can create a converging field. So what is the intensity? This is the field, and this is here. The field intensity is very much negligible. As the distance increases, then electric field is inversely proportional to R square. So it is also inverse square relationship between the electrical field and the distance. So as you go from that particular one along this direction or this direction or these directions, then the electrical field intensity decreases. So what is the amount of electrical field intensity at that point? So you have to place this one, a test charge at that point, and calculate the force. And this force due to this test charge is the electrical field. And the equation is 1 by 4 pi epsilon naught, and this value is 9 into 10 to the power of 9. Its magnitude. And the unit if you calculate, and this is so F equal to 1 by 4 pi epsilon naught. So this one is Newton meter square by Coulomb square. So this is Newton and then meter square by Coulomb square. So 9 into 10 to the power 9, this is the value, and you have to realize this one. And then potential. What is the about potential? So potential, if this is the charge, then it can create a field. And if we placed this, if we want to place this test charge from infinity to that point, then we can say that the potential at that point. So potential equal to work done by charge. Work done by charge, or you can take this one, then we can say that this is potential. So work done by the test charge is called potential at that point. Why the external agent does some work? Because there is a force between this and this one. And if you want to place this test charge from infinity to that point, then you have to do some work against the force. And this force, this work done, is stored as potential energy. Why? Because this is conservative in nature. What is conservative force? So electrostatic is a conservative one. So when the force is conservative, and if you do some work against this force, then this work done is stored as a potential energy within that particular body, and this is called potential. So work done by test charge, and this is called potential, and the expression is 1 by 4 pi epsilon naught and Q by R. So you have to know what is potential. So the expression is 1 by 4 pi epsilon naught Q by R, whereas the electric field is 1 by 4 pi epsilon naught and Q by R square, when the charge Q is kept at free space, within a free space, is kept within in a free space, or vacuum, free space. If it is a dielectric medium, then you have to divide this electric field with K. And what is about K? This is dielectric constant, and it can decreases the amount of interaction between the different charges. Okay, so all about this is the formula of all the numericals, that is from 34 to 38, are solved with the help of this one and this one, electric field and potential. Okay, so let's start with the first numerical, that is question number 34. And students, first of all, write down the numerical, and I think you are a genius one, so you can solve this one. Okay, so question number 34. The electrical force experienced by a charge of this one, so charge is given, and this is 1.0 into 10 to the power of minus 6, and this is Coulomb. And the electrical force experienced by a charge of 1. This Coulomb is this one, so force is also given, and this is 1.5 into 10 to the power of minus 3 Newton. So this is 1.5 into 10 to the power, force is given. Find the magnitude of electric field. Okay, so students, and the question is, you have to calculate the electric field. So electric field equal to force by charge, or force equal to Q into E. Oh yes, so you have to calculate electric field. So force is 1.5 into 10 to the power of minus 3 Newton, and this is 1.0 into 10 to the power minus 6 Coulomb. So 1.5 into 10 to the power of minus 6, when comes in numerator portion, then it is 10 to the power of 3 Coulomb. So minus 3 and plus 6 plus 3. So this is Newton by Coulomb. This Newton by Coulomb is the electric field within this region where the charge small q is kept. Okay, So 34 is completed and the next one is 35. The particle A and B having charges of these and these respectively are held fixed at a separation of 20 centimeters. So students, you can take these charges as Q and the another one is. So a charge of Q is kept here and this is point A, and another charge that is minus of 4 means it is minus of 2Q. 2Q, since it is 2 into 10 to the power minus 6, 2 microcoulomb, and this is 4 microcoulomb, so it is the double of this one, and held at fixed at a distance of, and this is 20 centimeter of separation, and this is B is given. Locate the points, not point, it may be a point or points, okay, and on the line AB, the electric field is 0. So students, you have to calculate the electric field where the electric field is 0 and the electric potential is 0. So where the electric field is 0, students, electric field is a physical quantity that tells about the force experienced by test charge. So it is F by Q naught. It means Q tends to 0. Q tends to 0. When the charges is very much negligible, and then this charge, what is the amount of electrical influence it gains, it experienced within the electric field, that is called field. So students, you have to place a test charge at various point within the field. So if we place here Q naught, then what is the electrical influence experienced by Q? So minus 2Q can exert a force along this direction, but the plus 1 is along this direction. So it is a situation where we can predict that electric field must be, it may be zero, because if this amount of force is equal of this one, then it is possible. But if we place a Q naught here, then this charge can repel this one along this direction, but this one attract this one. So it is not an equilibrium position, because all the forces are exerted along a specific direction, that is from A to B, and Q naught moves along this direction from A to B. Okay. Now if we place here, that is Q naught here, then this one can exert a force along this direction, but this one can exert a force along this direction. So it is a position where the electric field intensity, it may be again 0. So this is the static conditions where the test charge can possess the minimum potential, or the electric field is 0 at that point. Okay. So this is the case and this one is case, but where the electric field is 0. If we say that this point is 0 at that point, since this force, this is Q, this is minus 2Q, so the distance between these one is very much greater than amount of this one. So this force is greater with respect to this one. But for that particular cases, the repulsion force, this one is, this is the distance is less about this, but the charge is less amount of this, so the charge magnitude of this charge can compensate the distances. Here the repulsion force is greater because the distances is less as well as the magnitude of the charge, but at that point the distance is less for the value of the charges that possesses a minimum value with respect to this one. So this is the exact position. But this is not possible. So here it is not possible, but this is the, so you have to take here that this is the x distance from Q. So it is 20 centimeter plus x. So the electric field due to this one is proportionally constant, kappa into Q, kappa 1 by 4 by epsilon naught, that is kappa Q by x square. So x square, and this is equal to the EB equals to kappa Q means 2Q by This is 20, so you can write as 20 divided by 100 and then plus x, or you can take it as centimeter, because when we equalize this one, then it is in centimeters. So this is 20 and this is x, we can write, and then square. Okay, so then you get the answer as centimeter. Okay, so this is equation 1 and this is equation 2, and these are equal, so kappa q by x square, and this is equal to 2q by kappa and 2q by 20 plus x and then whole square. So q and q cancel this one, kappa cancel this one, so here it is 1 by x, here it is 1 by x, and this is equal to 2 means root 2 by 20 plus x. If we remove the square 1, so 20 plus x, so 20 plus x, and this is equal to root 2x. Okay, so root 2, when this one comes, then 20 equal to root 2 minus of 1 into x, or x equal to 20 by root 2 minus 1. So this is the exact position. This is centimeter and this is centimeter, and away from A, and since the electric field is a vector 1, so you have to mention the direction, that is from B to A. So along this direction, so from B to A, and the value is x equal to, and it is away from A, and the answer is, and if you divided this one, then you get 48.3 centimeter. Okay, so this one is 48.3 centimeter from A and along B to A. This is the directions of the electric field. And the next one is, you have to calculate the potential. You have to calculate the potential where the points where the potential is. Where the potential is. So this is q and this is minus 2q, and suppose there is a position here, the potential is this is the x distance from here. If we take this is the observation point, P, then the potential due to this one A, so potential due to A, and this is equal to this is positive charge, so this is kappa and q by x, 1 by 4 by epsilon naught q by x, and for this one, so this is B, and if you take in CH system, then you can easily write q by x in CH system, q by x, and this one is, and so this one is minus of 2q by 20 minus 6. So this distance is 20 minus x. The students, the equation is in CJ system, it is q by x, and in SI system it is kappa q by x, where kappa equal to 9 into 10 to the power 9. So VA equal to q by x and VB equal to minus 2q by 20 minus x, and if we take algebraic sum, then this is equal to 0, or you can easily write that q by x is equal to 2q by 20 minus x, or this plus this equal to 0, then it goes along this direction and takes the form of positive. So q and q cancel this one, so 1 by x, and this is equal to 2 by 20 minus x, or if we take a cross multiplication, then this is equal to, or 3x equal to 20, or x equal to 20 by 3. So x equal to 20 by 3. So 20 by 3 centimeter. Is it possible if the observation point is here? It may be possible, because this is the magnitude is greater and the distance for that particular one is a smaller one. Okay, so if we take a observation point is here and this is the x distance from Q, then again we can get a potential, zero potential at that point. So for that point there is Q by X. So the potential due to this one, VA equal to Q by X, and VB equal to minus of 2Q by 20 plus X. 20 plus X. This is the answer. Q by X. For that particular, if we take the observation point is here, then this one kappa Q by X, and if we take it is in CGS unit, then Q by X. Q by X and 2Q by this one. So Q by X is equal to 2Q by 20 plus X. 20. So Q and Q cancel this one. So 1 by X is equal to 1 by 20 plus X. 20 plus X. Sorry, this is 2. So 2 by this one. So 2x equal to, so 2x equal to 20 plus X, or X equal to 20 centimeter. So this is the answer. So 20 centimeter from A, or 20 by 3 centimeter between this position, between the midway between this, and it is away from A. So here it may be potential 0. So there are 2 points where the potential is 0. This one is an 1, and this one is the another points. Okay. So this numerical, the numerical number 35. Yes, it is 35 is completed, and the next one is 36. And the question is, a point charge produces an electric field of magnitude 5 Newton by Coulomb at a distance of 40 centimeter from it. Yes. And what is the magnitude of the charge? A point charge produces an electric field. So students, electric field is given. So the next one is, and the next one is question number 36. Question number 36, and here a point charge produces an electric field of magnitude. So electric field is given, and this is 5.0 Newton by Coulomb. So this is 5.0 Newton by Coulomb at a distance of 40 centimeters. So the distance is given 40 centimeter. 40 centimeter from it. What is the magnitude of the charge? So students, electric field equal to 1 by 4 pi epsilon naught Q by R square. Here you have to calculate the charge. So this is 9 into 10 to the power, and this is also given. So 5 equal to, this is 9 into 10 to the power 9 into Q by R square. R square is given, that is 40. So 40 by 100, and this is in centimeter. So you have to transfer this one into meter. SI system. So Q equal to, so Q, this and this cancel this one. So 2 2 is 4 and 2 5 is 10. So this is a 4, and this one is 10 to the power of something. So Q equal to, so Q equal to 5 into 2 2 is 4, and this is 5. So this is 9 into 10 to the power of 9 into this one. So this is 25. So this is 25. 5 5 25. So this is the answer, and the answer is 5 5 25. So 4 by 4 divided by 45 into 10 to the power of minus 9, and 4 divided by 45, that is equal to 0.0, and then if we take it as 8, then 3 6, that is 400. So 8 and 8 into 10 to the power of minus 9. So this is 8.89 into 10 to the power of this one 2, means 11. So 8.89 into 10 to the power of minus 11 Coulomb. 8.89 into 10 to the power of 89 Coulomb. Okay, students. So it is also a simple one, and the answer is yes, it is 8.9 approximate into 10 to the power of minus 11 Coulomb. Okay, the answer is correct one. So the 37, a water particle of mass 10 milligram and having a charge of this one stays suspended in a room. What is the magnitude of electric field in the room? Yes. So if we students think, if we place this chalk, is it an equilibrium? No, because the gravity acts along the downward direction. That's why the chalk falls down. So what is required? If a charge is given, students, here, and suppose mg act along this direction, then if this room can exert upward force, that is QE, if the electric field is E, then this charge, on this charge the force is QE, and if the force is equal to the weight of this one charge particle, then you can say that the charge is in equilibrium. So what is the direction? The direction, obviously, since a weight act along the downward direction, then the electric field is obviously along the upward direction. So you have to equalize this one. That is for question number 37. So for question number 37, you have to done this QE is equal to weight, because weight, due to this charge, weight act along this direction, and if there is electric field within this room, then on this chalk, if it chalk contains a charge of Q, the electric field along the upward direction is QE. So QE equal to mg, and all the values are given. So mass is given 10 milligram. So 10 into 10 to the power of minus 6 kg into 9.8 into 9.8, and QE equal to, so the electric field is 10 to the power of minus 5 into 9.8, or approximately you can take as 10 divided by Q. Q means 1.5. Okay, so Q means 1.50 into 10 to the power of minus 8, and this is Newton by Coulomb, or volt by meter, you can take as unit. What is its direction? It is in acts in the upward direction with a force of 65.3 Newton by Coulomb. Okay, the answer is 63. You can calculate it easily, I think. So that's why. For the next one is 38. So 38, question number 38 is a more interesting question. So 38 is, for board level, this question is enough one, but you have to take the concepts all the related with the AC Verma. Okay, so don't go through the process or numericals. You have to take the concepts. You have to grab the concepts related with every numericals. What is electric field, and what is potential, and how the electric field, where the electric, what is the conditions for the equilibrium one, where the electric field is 0, where the potential is 0, why you can get a two potential point is 0 but the electric field is intensities at a particular point is 0. So these all the concepts are related with this numerical. That is from 34 to 38, and the 31 is three identical charges and each having a value of this one are placed at the corner of an equilateral triangle of side 20 centimeter. Okay, and find the electric field and potential at the center of the triangle. Okay. So students, the numerical is question number 38. This is the last one, question number 38, and this is the last one, and 38. Three identical charges, students, three identical charges. So Q, Q, Q are placed at an equilateral triangle at each and vertices. Okay, so you have to calculate electric field here. So the electric field is 0 because these charges can exert a force along this direction, and these charges can exert a force along this direction, and the resultant is along this direction, and these charges can exert a force along this direction. So when this force is equal to this one, then the net effect is 0, since all the particles, all the charges are kept along a symmetric position. Suppose, student, there is a charge and there is another charge and there is another charge, and you have to calculate electric field here. So this one is exerted along this direction, this one is along this direction, so the resultant is along this direction can exert a force, so the resultant is not 0. But here all the points are in symmetric condition, so if we calculate electric field at that point, then the electric field is 0. But potential is not 0. But the potential is not 0, because to calculate the potential you have to know this one. If it is a site is A is given, suppose the site is x, so the height is root 3 by 2 into site. So this is the expression, we know that from 7th standard, the height of the equilateral triangle. So this one, and this can cuts 2:1 ratio. So this is 2/3 of this one, and this is 1/3. So 2/3 of this one is equal to, so this is the total height, and the 2/3 of this one, 2/3 of this one, and if we cut into 3 parts, then this is 2:1 ratio. So it can cut a 2:1 ratio. So this is 2/3 of this one, and this is 1/3. So 2/3 of the total height. This is the formula for the height of the equilateral triangle. So this is 2 and 2 cancel, and this is 1 by root 3 into x. Root 3, and this is cancel this one. So the distance is, this one is x by root 3. So the potential is, so the potential due to, suppose this is A, this is B, and this is C. So VA equal to kappa, and then Q by, this is the charge, and Q by distance. So x by root 3. And for VB it is also equal. This is equal to VB, and this is equal to VC. So the net potential is VA plus VB plus VC, and that is 3 into this one. So 3 root 3 Q by x into kappa. Kappa means 9 into 10 to the power of 9, and this is the potential. And you can put the value of x, it is in centimeter, I think, and Q is also given. So Q is also given here, 31. Q is 1 into 10 to the power minus 8. So 1.0 into 10 to the power minus 8 coulomb, and this is 20 centimeters. So the answer is 9 into 10 to the power of 9 into 3 root 3 into Q, that is 1.0 into 10 to the power minus 8, I think. Yes, it is divided by x, and the x is 20 centimeters, so 20 by 100. And this is this board. This is 38. And the student's answer is 2.3 into 10 to the power of 3 volt. So this is 2.3, and you can check the answer after calculating. You can check this one, and this is volt. 2.3 into 10 to the power 3 volt. Okay, students. And students, I think all the numericals I try from my heart, and I try my best one that is given to you always. So all the numericals, that is from 34 to 38 is completed, and I think you realize a better one, and the students try to grab the concepts related with this, and stay with me. And this is a very conceptual, and this is numerical based channel. Okay, so if you feel problems in numericals, then stay with me and subscribe this channel, and most of all like it and share it with your friends. Okay, so thank you, and last of all I want to say, continue your study. Thank you.